Welcome back to the deep dive. Today we are getting, well, truly fundamental. We're going to be stripping complexity down to its absolute bare bones.
We really are.
We're venturing deep into the world of graph theory. This is the math that, defines how everything is built, from your computer network to social structures.
Everything. And our focus today is really on three things.
Yeah.
Navigation, structure, and vulnerability.
And finally, the search for that perfect, most efficient architecture possible, the tree.
Exactly. We've got a stack of sources here that are, let's say, heavy on the formalism.
Yeah.
Very algorithmic.
So our mission is to pull out the core concepts.
That's the plan. We want to define what it means to move through a network, figure out how to pinpoint its weaknesses, and then understand what optimization really means in purely structural terms.
The goal here is that by the end of this, you, our listener, will understand the exact mathematical skeleton that underlies efficiency in, well, any complex system you can think of. Okay, let's jump right in. The language of navigation. If we're going to talk about how things are connected, we have to be incredibly precise about our words.
Oh, absolutely. The difference between just, wandering around and taking a specific, efficient route is mathematically crucial.
And our sources hammer this point home right away. There's even a warning in the original German.
Achtung bei der Literatur.
Which means?
Beware the literature. It's a warning that this terminology is a mess out in the wild. Different books, different papers, they use these words differently. But we're going to stick to our sources' definitions.
Holding the line. So what's the first term?
The first and most basic type of movement is called a Kantenzug, or fad. In English, you'd call it an edge sequence or a trail.
Okay, a trail.
Think of it as just a sequence. Vertex 1, vertex 2, edge 2, and so on. The key thing here, the absolute main takeaway, is that you are allowed to repeat things.
Repeat things how?
You can revisit the same vertex multiple times. You can even walk back and forth along the same edge if you want.
So it's like wandering aimlessly through a city. You might walk down a street, realize you forgot your wallet, and walk right back down the exact same street.
Precisely. It's a description of travel, not an efficient route. It doesn't care about redundancy at all.
It's just a log of where you've been.
Exactly. Now, the second type of movement is where it gets mathematically interesting. This one is called the WEG, a path.
A path. Okay.
And our source material mandates that when we say WEG, we mean a simple path. And here's the rule. In a WEG, all vertices must be distinct.
Ah. So no repeats. If you visit node A, you can never, ever come back to node A later in that same path.
That's it. It completely eliminates loops, it eliminates backtracking. It's a clean, one-way journey.
So why is that distinction so important?
Well, think about algorithms. If you want to find the shortest distance between 2 points, you have to use a WEG. If you allowed for a fad, a trail, you could just loop around a cycle forever and create a path that's infinitely long.
Right. It wouldn't make any sense.
The WEG guarantees we're measuring a real, non-redundant connection.
Got it. So if you want the GPS directions from New York to LA, you're looking for a WEG. If you're just tracking a delivery truck that might have to double back, that's a PFAD.
Perfect analogy. And that brings us to the third and final type of movement, which is all about structure. It's the crease. A cycle or a circuit.
A cycle, so it goes in a circle.
Pretty much. It's a path that starts and ends at the same vertex, but, and this is the important part, just like a simple path, it contains no other repeated vertices. It's a closed loop.
Okay, that's clear. And the final piece of vocabulary, length.
Ah, yeah, length is the easy one. It's just the number of edges you used. Simple count. If you walked along 10 edges, the length is 10.
Whether you were wandering or taking a direct route.
Exactly. The length alone doesn't tell you about efficiency without knowing what kind of path it was.
Okay, that sets the stage perfectly. We know how to talk about movement. So the next logical step is to look at the whole network, the whole city map, not just one trip.
Right. We need to assess its resilience, its robustness, which takes us into our second section, the architecture of vulnerability.
How do we figure out if a network is strong, and maybe more importantly, where are its weak spots, its single points of failure?
We have to start with the most basic question of all. What does it even mean for a graph to be connected?
Right.
The definition is pretty intuitive. A graph is zusammenhängen connected. If you can find a path, a WEG, from any node to any other node.
If you can get from anywhere to anywhere else, it's connected.
Simple as that. And if you can't...
Like you've got islands.
Exactly. If the graph is disconnected, it breaks apart into these separate pieces. The source calls them Zusammenhangskomponenten. connected components.
So you could have a big corporate network, but if I don't know, the marketing department server can't talk to the accounting department's server.
Then in two different connected components. That's right.
Okay. This idea of components leads to a really interesting bit of math, Lemma 3.2.5. It's about the absolute minimum requirement for things to be connected.
It is. It's a fascinatingly simple formula. It states that for any graph with v vertices and e edges, it must have at least v minus e connected components.
V minus e. So you just subtract the number of edges from the number of nodes. That seems weirdly simple. How does that work?
It's a really beautiful, constructive proof. Let's build a graph from scratch. Imagine you have v vertices, just dots on a page, but 0 edges. E equals 0.
Okay, so you have v separate islands, v component.
And the formula holds right. V minus 0 is v.
Right.
Now, every time you add one edge, what's the best you can possibly do to reduce the number of islands?
Well, you can connect two of the islands. That merges them, so the number of components goes down by 1.
Exactly. You can reduce the component count by at most 1. Sometimes if you add an edge between two nodes that are already in the same island, the count doesn't change at all.
Okay, I see. You can never connect 3 islands with 1 edge. So you only ever reduce the island count by 1 or 0?
So after adding e edges, the absolute best case scenario, the fewest components you could possibly have, is your starting number, v, minus the number of edges you added, ev minus e.
So this is like a quick sanity check for a network designer. If you have 1,000 nodes, but only, say, 500 edges, you know for a fact you have at least 500 disconnected components. Your network is guaranteed to be fragmented.
It's an instant structural check. It tells you if you've even spent enough on connections to have a chance at a cohesive network.
That's a great foundation. But we know that even a fully connected graph can be, well, fragile. There can be bottlenecks.
Right. Not all nodes and edges are created equal. Some are carrying a much heavier structural load. There's the single points of failure.
We have names for these. The first one is the articulation node, or articulation snowden.
This is a node, a single point, whose removal would cause the graph to break apart. Or, more formally, it increases the number of connected components.
Give me an example.
Think of a country's power grid. If there's one single central substation that links the entire eastern half of the grid to the western half, and no other way for power to cross, that substation is an articulation node.
If it goes down, the lights go out for half the country, or at least they become 2 separate grids.
Exactly. It's the linchpin. The second type of weak point isn't a place, it's a link. It's called a bridge, a brooka.
So this is an edge.
Yes. An edge whose removal causes the graph to fall apart. Imagine a supply chain where the only way to get goods from the factory to the port is over one specific bridge across a canyon.
If that bridge washes out, the supply chain is broken. That edge is a bridge.
That's the one. So the articulation node is like the central server. The bridge is the single fiber optic cable connecting two data centers. Both are critical failures.
Okay, so to make this idea of fragility more abstract, I guess, we have this concept of a cut.
The Schnitt, yes. A cut isn't a physical thing in the graph. It's a conceptual tool we use to measure connectivity.
How does it work?
You just imagine partitioning all the vertices, V, into two groups. We'll call one group S, and the other group is just everything else, the rest of V.
So you just draw a line on your map and put some cities on one side and the rest on the other.
Exactly. And the cut edges are all the roads that cross that line you drew. All the edges that go from a node inside S to a node outside of S.
And this leads to another really important insight, Lemma 3.2.9, which gives us the ultimate test for connectivity.
It's a powerful one. It says a graph is connected if, and only if, every possible way you can cut it into two non-empty pieces.
Every possible line you can draw
results in a non-empty cut. There must always be at least one edge crossing the boundary. No matter how you slice it, the two halves have to be connected by something.
So if I can find even one way to slice the network where 0 connections cross the line, the whole thing was never truly connected to begin with.
That's the practical test. And the proof is this really elegant piece of logic. It uses the contrapositive.
Okay, let's walk through that. It sounds important.
So let's assume the opposite. Assume the graph is not connected. What does that mean?
It means there's at least one pair of nodes, let's call them S and T, that you can't get to from each other. There's no path.
Perfect. That's our starting point. Now let's define our set S. We'll say S is the set of all the nodes that you can reach from our starting node, S.
Okay, so S is like S's entire neighborhood, everything it's connected to.
And since we know that S is unreachable from S,
To T can't be in S. It must be in the everything else pile.
right. So we've naturally partitioned the graph into S, the part reachable from S, and everything else, the part that's not. Now let's look at the cut. Can there be any edge that goes from inside S to outside S?
No. Because if there were an edge from some node in S to some node outside S...
I call them S prime and T prime.
Right. If there was an edge from S prime to T prime, then you could get to T prime. You just go from S to S prime, and then take that one last edge to T prime.
Which would mean G prime is reachable from S.
But if it's reachable from S, it should have been in the set S in the first place.
That's the contradiction. So if a graph is disconnected, there must exist a cut with 0 edges. Therefore, the reverse must be true. If every cut has at least one edge, the graph must be connected.
That's really solid. It's a guarantee.
Okay, so now we have the tools. We know what paths are, we know what weakness looks like, and we have a way to prove a network is solid. This feels like the perfect setup for the next question.
Which is?
What if we wanted to build the ideal structure? A network with 0 redundancy, optimized only for cost. The perfect network.
Then you want to build a tree.
Section 3, the ideal structure.
Trees really are the gold standard for efficiency in network theory. They give you the absolute maximum connectivity for the absolute minimum cost.
So let's start with the definitions. The first one is actually a forest, a walled.
Right. A forest is a very simple concept. It's any graph that has no cycles. It's kreisfrei. If you can't find a single closed loop anywhere in the drawing, you've got a forest.
And it doesn't have to be connected.
Nope. A forest can be a bunch of separate, disconnected pieces, as long as none of those pieces have loops. And a tree, a bomb, is just a connected forest.
That's the definition. A tree is a graph that is both connected, A and D, has no cycles. And that combination is what makes it so powerful and so efficient. The name makes sense too, right? A collection of separate trees is a forest.
It does. And what about the endpoints? The dead ends of a tree.
We call those leaves, bladder. A leaf is just a node that has a degree of exactly 1. It's only connected to one other node.
Yeah.
It's the end of the line.
Now, there's a really cool observation here. It says every finite tree with at least 2 nodes has to have at least 2 leaves. Why 2? Why not just 1?
You can't build one with just one. The structure itself forbids it. Think about it. You start at any node and just start walking.
Okay.
Since there are no cycles, you can never revisit a node you've already been to. And since the graph is finite, you can't walk forever. You have to stop somewhere.
And the place you stop has to be a dead end, a leaf.
It must be. And to find the second one, you just, conceptually walk the longest possible path through the tree. You are guaranteed to start at one leaf and end at another.
That's neat. And the structure is also inherently stable in a way. The next observation says if you snip off a leaf, what's left is still a tree.
Right. You haven't broken the core connectivity of the rest of the structure because that leaf was only attached at one point.
Okay, this brings us to what feels like the main event of this entire deep dive. SATS 3.3.4, the power of equivalence.
This is one of my favorite theorems in all of graph theory. It's so elegant.
It gives us 5 completely different ways to describe a tree, and it says they are all mathematically identical. If you can prove one of them is true, you've proven all of them.
It's the network designer's ultimate toolkit. You just pick whichever property is easiest to check for your specific problem, and you're done.
Let's go through them. The first 2 are all about the number of edges, the cost.
Right. Property 1. A graph is a tree if it's a cyclic, no cycles, and has exactly n1 edges, where n is the number of vertices.
And property 2 is the flip side. A graph is a tree if it's connected and has exactly n1 edges.
See the power there. That number, n1, is the magic number. It's the absolute minimum number of edges you need to connect n things. If you have that many edges and you're connected, you're guaranteed not to have any cycles. If you have that many and no cycles, you're guaranteed to be connected.
It's the mathematical definition of maximum efficiency. Every single edge is doing essential work. There is 0 slack.
And that idea of no slack is captured perfectly in the next 2 properties, which are about minimality and maximality.
Okay, property 3, minimal connected.
A graph is a tree if it's connected, but if you remove any single edge, it falls apart.
Whoa, wait, let me process that. So this means that every single edge in a tree is, by definition, a bridge.
Every single one.
So in the quest for maximum efficiency, for this perfect N1 structure, you have simultaneously created a system with maximum fragility. Every link is a single point of failure.
That is the fundamental trade-off of the tree structure, baked right into the mathematics.
Yeah.
Efficiency versus resilience.
That's a huge insight. Okay, what's the other side of that coin? property 4.
Maximal acyclic. This says a graph is a tree if it has no cycles, but if you add any single new edge between two existing nodes, you are guaranteed to create a cycle.
So the structure is completely taut. It's stretched as far as it can go without looping back on itself. You've used up all the non-redundant connections possible.
Exactly. Properties 3 and 4 are just two ways of looking at that same N1 edge count. You have just few enough edges to avoid loops and just enough to stay connected. Add one or take one away, and it's not a tree anymore.
Incredible. And the final property, number 5, brings us back to where we started, back to navigation.
It does. Unique path. A graph is a tree if and only if, for any two vertices in the graph, there is exactly one unique simple path, one WEG between them.
No alternate routes.
None.
This is why things like a file system on a computer are trees. There's only one way to get from the C drive to your document. There's no ambiguity. It makes finding things incredibly simple.
It reduces routing to a trivial problem. The path is predetermined. So you have these 5 different lenses: edge count, connectivity, vulnerability, loop avoidance, and path uniqueness, and they all describe the exact same perfect, efficient structure.
Okay, so we know what this ideal skeleton looks like. The practical question is, how do we find it? If I have a messy, real-world network with lots of redundant connections, how do I extract this perfect tree from within it?
An excellent question. And that brings us to our final section. Section 4, spanning trees.
The span bomb. What does spanning mean here?
A spanning tree is a subgraph. That means it only uses the original nodes and edges from your messy network. And it has 2 key properties. It includes all of the original vertices it spans across them, but it has been thinned out, aufgedünnt, to remove redundant edges until what's left is a perfect tree.
So you take a dense, interconnected city grid and find the absolute minimum set of streets you need to keep open to make sure you can still get from any intersection to any other intersection.
That's the perfect way to think about it. And we know it's always possible. Any connected graph is guaranteed to have at least one spanning tree.
How do we know that?
Well, a simple proof is just you start with your messy graph, find a cycle, and throw away one edge from that cycle. The graph is still connected, right?
Yeah, because there was an alternate route.
So you just keep doing that. Find a cycle, remove an edge. Find another cycle, remove another edge. Eventually you'll run out of cycles, and what you have left must be connected and acyclic. It's a tree.
But that sounds a bit random. We need a systematic way to do it, an algorithm.
We have 2, and they are both based on a very simple, very powerful idea: the greedy algorithm.
Greedy, meaning?
Make the best-looking local choice at every single step and hope it leads to the best overall solution. For spanning trees, it just so happens that this works perfectly.
Okay, let's look at the first approach, the one that's usually preferred, greedy in.
This is a Kruskal-style algorithm. The strategy is to build the tree from the ground up. You start with nothing, an empty set of edges.
And then you just start adding edges back in.
One by one. You look at all the available edges in the original graph, and for each one you ask a simple question. If I add this edge to the tree I'm building, will it create a cycle?
If the answer is yes, you don't want it. It's a redundant connection. You reject it.
And if the answer is no, you greedily accept it. You add it to your collection and move on to the next edge.
And how do we know this actually works, that it gives us a tree in the end?
Because it ties directly back to those equivalent properties we just talked about. When the algorithm stops, what you have a collection of edges where you can't add any more without creating a cycle.
That's property 4. Maximal acyclic.
Which means it must be a tree. And since it spans all the vertices, it's a spanning tree. The logic is airtight.
But the efficiency, that's the key, isn't it? The source says this can be done very fast, like ON2. How do you check for a cycle so quickly every single time? That sounds hard.
It would be if you actually search for a cycle. But there's a brilliant trick. You don't look for cycles. You just keep track of your connected components.
Back to the islands.
Exactly. You start with n islands, one for each vertex. Now, when you consider adding an edge, say from node U to node V, you just ask a much simpler question.
Which is?
Are U and V already in the same component? Are they already on the same island?
If they are, that means there's already a path between them. Adding this new edge would create a second path, which makes a cycle. So you reject it.
Right. And if they're in different components, adding the edge connects those two islands. It merges them. It can't possibly create a cycle. So you accept the edge and you update your data to say these two islands are now one bigger island.
And that lookup, checking which island a node is in, that's fast.
It's incredibly fast. That's what makes the whole algorithm practical and efficient. It's a simple local check.
Okay, that makes sense. But there's another way to be greedy. Instead of building up, we can tear down.
The opposite philosophy. Algorithmic approach 2. Greedy out, pruning the network.
So here we start with the entire messy graph. All the edges are there.
And we iterate through the edges one by one, but this time we ask the opposite question. Is this edge absolutely necessary?
How do you check that?
You ask, if I remove this edge, does the graph stay connected?
If it does, that means the edge was redundant, it was part of a cycle, so you throw it away.
You prune it. But if removing the edge would break the graph into two pieces,
Then it must be a bridge. It's critical, you have to keep it.
and you keep doing this until every single edge you have left is a bridge.
Let me guess. This ties back to another one of our properties.
Property 3, minimal connected. The final graph is connected, and every edge is a bridge. By definition, it's a tree.
So mathematically, both algorithms get you to the same place. But there's a huge but here when it comes to performance.
A massive one. The sources note that greedy in is fast, ON2. Greedy out can be brutally slow. We're talking ON4.
And for anyone listening, that jump from n squared to n to the fourth it's not a small step. It's the difference between an algorithm finishing in a second and one that could run for hours or days on the same input.
It's a catastrophic difference in performance. And it all comes down to the cost of the check at each step.
In greedy in, our check was local and fast. Are these two nodes on the same island?
Yes. A simple lookup. In greedy out, every time we think about removing an edge, we have to verify the global connectivity of the entire remaining graph.
So you have to run a whole new traversal, like a search algorithm, across the whole network just to make a decision about one edge.
And you might have to do that for every single edge in the original graph.
So it's like the difference between looking up two names on a list versus having to resurvey an entire city's road network every time you consider closing one street for construction.
That's a perfect way to put it. The lesson is that sometimes the inverse problem, figuring out what to throw away, is computationally way, way harder than the direct problem of figuring out what to keep.
What an amazing journey. We've gone from the simplest definition of a walk to these highly efficient and sometimes not so efficient algorithms for finding a network's core skeleton.
Let's quickly recap the main takeaways.
Please.
First, vocabulary is king. The difference between a general fad or trail, which can have repeats, and a simple weg or path, which can't, is the foundation for everything else.
Then we learn to spot weakness. The single points of failure, bridges are the critical links, articulation nodes are the critical places.
And we learn that the cut is the mathematical tool that gives us a rock-solid guarantee of connectivity.
And then the star of the show, the tree. This remarkably efficient structure, which we learned can be defined in 5 equivalent ways.
Right. Whether you define it by its N1 edge count, its minimal connectivity, its maximal acyclicity, or the fact that it has a unique path between any two nodes, it's all the same elegant structure.
A structure, as we noted, where maximum efficiency means maximum fragility. Every edge is a bridge.
And finally, the greedy algorithms work perfectly to find these trees because their goals being maximal acyclic or minimal connected map directly onto the properties of a tree. But building up is just so much faster than tearing down.
Which brings us to our final thought for you, the listener. This inherent trade-off, this tension between efficiency and fragility, is something we want you to think about.
We've established that trees give you maximum bang for your buck, right? The minimum N1 edges to connect everything.
Yeah.
But that comes at the cost of zero resilience. Every connection is a single point of failure.
So the question we leave you with is this. If you were designing a real-world network, a national power grid, a financial trading system, a logistics network, how would you use this knowledge?
Where would you insist on the brutal cost-saving efficiency of a tree-like structure? And where would you deliberately spend the extra money to add redundant edges to create cycles purely for the sake of robustness? How do you decide which connections can't be allowed to be bridges?
That's the real engineering problem, isn't it? The balance between cost and safety. Something to think about as you navigate your own complex systems this week.